Okay, hi everyone. Just waiting for the YouTube to start. Um, this is another in a series of lectures where what I'm trying to do is give some background to people who hopefully are going to work together on some further calculations in group cohomology. But it so happens that well, I want to just record these so people can watch them on their own, and this is how I know to do so. And B, in this case, and I think this will continue to be the case, I might as well be fairly self-contained, trying to, with these kinds of stories, with a cohomology of symmetric groups, which is this basic calculation that we've made a lot of more progress on in the last decade than we had before. There's a lot of pieces to the story, but making each one self-contained, sort of its own little small meal rather than this big buffet is, I think, the approach that makes sense in general. So yeah, so what we're going to do today is a bunch of algebra, although you'll see that some quote-unquote geometry, more in the symbolic sense than the actual thinking about, say, manifold sense, comes into play. So, so a Hopf ring is a group object. Let me just give one definition: a group object in the category of coalgebras. And note that it's a ring object, of course. The group objects in the category of coalgebras, that's often called a Hopf algebra. The monoid objects are bialgebras. So, but really, it would be nice to call these Hopf monoids, Hopf groups, and then everybody would know what a Hopf ring was, but that's not how history is developed. But our goal today is to just make them fairly concrete in a nice case of interest where you can get your hands on absolutely everything. And that is with symmetric functions. So let's just start with more familiar ones. And the point is that there's a second product on symmetric functions. So let me just give an example. And this is on second symmetric functions with possibly different numbers of variables. And so what we do, here's a little example, is we take a symmetric polynomial, like say x1, x2, x1, x3, and take another one with maybe different numbers of variables. And this is going to be defined to be, I'm going to induce up. You could also say fully symmetrize, but to be consistent and suggestive, talk about inducing up what I get when I just take the product. And I'm going to take the product first reindexing. So the first set of variables is 3 variables. The second is 2. So instead of calling those x1 and x2, I'm going to call those x4 and x5. And so . you can make this, you can do this multiplication. It would have 6 terms. I'm not even gonna. And then you have to induce up, and you'd see that in this case, you know, I'm just getting things where, you know, 1, 2, 3 sort of are invariant in those sort of internal ways, and 4 and 5 are invariant. So to make them fully invariant, well, you see what these monomials are, so it shouldn't be too surprising that I get the sum of just all possible ways to multiply 3 of the base variables. Okay, so that's a little example, a way to take a symmetric function in 3 variables and 1 and 2 variables and make a symmetric function in 5 variables. It also works with multiple sets of variables, and this is where the story becomes much more interesting. And again, let me repeat that normally multiplication on symmetric polynomials just fixes the same number of variables, and this is going between. It's easy enough to formalize. Just a multiplication on a multiplication map on tensor product, of course. Right. So we can also look at multiple sets of variables. What I'm going to do in general, instead of using multiple indices, is going to have a set of variables x, another set of variables y, maybe z, w, whatever. And so here's a symmetric polynomial. And maybe I want to take this new product with, here's another symmetric polynomial, again, just 2 variables. The first one is in 3 variables, and I'm once again going to get, I'm going to have to induce up. What I get when I take, well, the first term is going to be x1, y1, and then the x1 squared becomes an x4 squared. And then you see that in general, I've got one x variable to the first power, that same corresponding y variable to the first power, and then an x variable to a different power. So you can look at this as a sum of xi, yi, xj squared, not equal to j. Let me make it clear, my i's and j's. Okay, all right. So these rings in multiple variables are a lot more interesting. So we're used to the fact, so while so while k, x1, xn, Sn is polynomial for any k, no relations. We see, for example, if I take f2 and look at 2 sets of variables, and again, the S2 action is going to switch the indices rather than the variables. So 2 sets of variables, each with, say, 2 variables. Then I claim that this is generated by, let's list a few things. So I can have x1 plus x2, y1 plus y2, x1, x2, y1, y2, and I'm going to present this in a symmetric way. So I'm going to take two things, two generators, even though you'll see I only need one. So one is x1, y1 plus x2, y2, and the other is this more interesting one, perhaps. Maybe not really, but okay. And then we have A, B equals E plus F in this case. So this is just little calculations you can make. So I could just take E or F as a generator, but I like to take them both because then E times F is A squared D plus B squared C. So this is about as small an example as you could imagine, and you get relations. And these numbers of relations just explode as the numbers of variables get large, and both the sets of variables and then the number of variables within each set of variables gets large. So it's a hard thing to tame, and again, the point is going to be to give one way to tame them. So an important auxiliary structure, related structure, kind of similar in flavor, is a coproduct, where you take your symmetric polynomials. I'll just say it in one set of variables, but it works. Symmetric polynomial in n plus m variables. If it's symmetric in n plus m variables, I can forget the symmetry down to the fact is that it's symmetric over n and n variables, m variables separately. And there's a standard way then I can kind of decompose additively any monomial in n plus m things to as a product of a monomial in n things and a monomial in m things. So and then the invariance remains on those two factors. And so this is what we could call a coproduct. Of course, this is isomorphic to the second factor is isomorphic to just the usual indices on those variables. And then the theorem is that the usual product, the standard product on symmetric polynomials, that is the one that just takes symmetric polynomials with the same number of variables and just multiplies them, and you have something invariant still, distributes over this induction product through with respect to the coproduct. The coproduct is part of this distributivity. That is, if I take a symmetric polynomial and want to multiply it by one of these symmetric polynomials obtained as an induction product. So say f has n plus m variables, g has n variables, and h has m variables. Then I'm going to take the sum over the coproduct, and maybe the coproduct I emphasize. I just really care about the piece with n variables and m variables, as I'm forgetting. And if I take the coproduct of f, and that ends up being, say, the sum of ai tensor bi, I'm going to take ai times g. They're symmetric polynomials of the same numbers of variables. I can multiply them, and bi times h, and take that induction product. Okay, so let me once again give an example of what this looks like. And by the way, this is the use of these symmetric polynomials as a sort of a base case for understanding the Hopf Rings structure on cohomology of symmetric groups is what Paolo, Salvatore, Chad Giusti, and I that's the approach we took in our first paper in this area, because it's actually more than a formal connection. There's maps between them, these key examples that and the cohomology of symmetric groups that we elaborate on. Okay, so in the example, our f is going to be, say, x1 squared y2 plus x2 squared y1, and let's multiply that by our g is going to be x1 cubed times our h, which is going to be, and this is again this induction times say x1 y1. So one thing we can do is just perform that induction product. And that's simple enough because I get x1 cubed y x2 y2. Then I have to symmetrize that, and so that's x2 cubed x1 y1, if you will. Great, and I can multiply that out, and I get this. And these are the same, so I really have two of these. All right, let me scroll so you can check my arithmetic. Great. So that's one way of doing this calculation, and then what you hopefully appreciate is that via the coproduct formula, we have to, well, let's look at the coproduct of f. And that ends up being, say, x1 squared tensor y1. That's the 1-1 coproduct. We only have one set of variables in each g and h, and so even though f has two sets of variables, we sort of restrict to pairs of one sets of variables, and then of course it's the invariance is easy to see. It's trivial. But then we also have y1 tensor x2 squared. Okay, great. And so then in the formula, so then the sum over delta f of ai times g induction product with bj times h ends up being what? Well, we get x1 squared x, let's see, x1 cubed, right? Induction y1 x1 y1. And then the next term in the coproduct gives us x1 cubed y1, induction product x1 squared x1 y1. And what we see is that the induction product of these pretty quickly lead to this term and its sort of symmetric partner, which is off the screen right now. But whereas this, its symmetrization, notice that it's just x1 cubed y1, induction x1 cubed y1. It's a funny induction product. It ends up being symmetric to begin with. And so you get two terms once you symmetrize. Right. So that's an example of how this this works. Start to see a little bit that the terms you get with the coproduct seem to be simpler in this than quote unquote doing out the algebra. Right. And so notice that in general, we have, as in here, so in general, f times f is going to be twice something. Because there's already this S2 symmetry to begin with. And so maybe I didn't say it appropriately before, but when I induce up, if I induce up from something which has this S2 symmetry, I'll be able to match the terms in the induction up for a factor of 2. The other way to say it is that because f sort of right before induction, f times f is invariant with respect to sort of an S2 wreath Sn rather than just Sn cross Sn. The wreath product switches the two factors as well, whereas Sn cross Sn preserves those blocks. So what I wanted to discuss now, to introduce another key piece of terminology. This is not in the original paper with Chad and Paolo. It's something that is being developed with Paolo and Lorenzo. This is an example of divided powers. So there's a divided powers structure around, and these are really just, and you can formalize this, rings. What is a divided powers algebra? It's rings which support the series e to the x Taylor series for e to the x means that for any x, I've got an x squared over 2 factorial, x cubed over 3 factorial. In other words, there's things which when I multiply by 3 factorial, I get x cubed. When I multiply by 4 factorial, I get x to the 4th. They also end up being the duals of primitively generated polynomial Hopf algebras. So that's the key for us. In topology, probably the first example, they come up with sort of, again, there's some symmetric groups. I mean, e to the x, you've got n factorial is the order of the nth symmetric group is part of the definition. And so you've got basically homology and cohomology of things like symmetric products, configuration spaces. And actually Eilenberg-MacLane spaces, and that's the first example I wanted to discuss. So let's look at RP infinity. So that's just the classifying space for the group with one non-trivial element. And here is how I like to think about RP infinity sometimes. This is the simplicial bar construction. This is discussed, for example, in the first YouTube series I did. This is again, a simplicial model. And and if you want, you could have the non-trivial element labeling things here. And if a G goes off the end, it disappears. If two G's come together, they vanish because their product would be E, and anything labeled by E vanishes. And then one advantage of this model is that it is an abelian group itself through juxtaposition. So if I maybe I'll have the very first ones line up. And if I take the sum of two things, I basically take the union on the same number line. But if 2 points line up, I multiply them. Implicitly, by the way, I can say there's an E here if I want to multiply it everywhere. If I want to think about the multiplication everywhere, right? And same kinds of identifications give us, well, it's going to be 4 G's. So that's one way to think about RP infinity. I think this might actually be homeomorphic, but I've never checked. It is at the 2 skeleton level. This has, the reduced realization has is just a cell complex with one cell in each degree, namely the cell. The cell where, so in fact, let's say cells equals mod 2 homology representatives as usual. Our xi is where I'm going to take I points on the interval and put my g's there. So it's parameterized naturally by delta I, because that's the set of I increasing points. And then, so of course, x1, I'm just seeing G move across. And then here's the point that x1, if I take the induced map on homology from this addition, it gives me multiplication in homology. And then, for example, x1 times x1, well, I'm going to, have one G going every possible way and another G going every possible way. And that looks like the picture for x2, but really these sort of are free to pass each other. So this ends up being 2x2, because for every picture in x2, there's exactly two ways I could get it as a product of things in x1. So, and in general, you can see that the product in homology of xi and xj is going to be this binomial coefficient of shuffles times xi plus j. And the way then to say this is that the homology of RP infinity with my two coefficients is the free divided powers algebra on a class X, which is our X1. So you might call Xi, think of it as X divided power, and I'm going to start being in the habit of having my divided power as subscripts. It's just more convenient in the Hopf ring setting. This, by the way, ends up being over F2, just exterior on classes X to the I. Because I need, so I've got X1 times X1 is twice X2. So X2 is non-zero. I need it in there. Twice it is this product, which ends up being 0, because 2 is 0. But X3 is, say, 3 times X1 times X2, because of that binomial coefficient. So I don't need X3. And then you quickly see that the product of any of these xi's times themselves is 0. Again, this is all mod 2. Okay. So, so with this additional structure, so I haven't defined a divided powers algebra, but well, this formula for xi times plus xj is sort of a basic. You just have you have these for every class for every element of your algebra, you can take its ith divided power and whatever you want to call that. And these divided powers, when they multiply according to exactly this shuffle binomial coefficient product rule. Okay, so let's get back to our main story. And that's, again, trying to understand Hopf rings in the special case of symmetric polynomials. So we're gonna, just to make our lives just shorter to explain everything, a rig is a ring without negatives. Remember that, of course, usually in a ring, the multiplication is allowed to be a monoid. In a rig, the addition can be a monoid as well. Then the theorem is that if I look at symmetric polynomials in any number of sets of variables, and I'll just, again, rather than using multi-indices, I'll just say I go to some last set of variables, we'll call omega 1 to omega n. if I'm then looking at the things which are invariant as I permute the x's and the y's and the omegas among themselves and everything else in between. And then if I look at those all together, and let me just say, this is with the product as usual on a direct summand, but for purposes of clean statements, we'll extend it to 0 between summands. So that's kind of like in computer programming. If I try to multiply a symmetric polynomial in 2 variables with 1 and 4 variables, the compiler says doesn't work, but actually returns 0. Sorry, instead of saying doesn't work. And let's just remember that we have our induction product and our coproduct as above. This is the free divided powers Hopf ring generated by the simplest classes you can think of, namely x1. If n equals 1, that's a symmetric polynomial in 1 variable, or y1, or up through omega 1. And we need the units in each. And it's Hopf ring generators. They don't sort of come for free, or we could define them to come for free, I suppose. Okay, so I gave you a little example with n equals 2 and 2 sets of variables, and said there's a lot of relations, or some relations already, and then you get more and more relations and a lot of combinatorics to try to somehow understand these as commutative rings. But if you understand all of them together, the direct sum, each is a summand of this larger structure. I've got this induction product between them, and those two products together are fairly well behaved. The other way to say this is that all relations informally, all relations follow in, follow from Hopf ring distributivity. And the divided power structure. And the fact that it's 0 multiplication between what we often call components. Okay, so what I wanted to do was go back to some of the other, my first calculations, in light of a sort of a graphical approach to this structure. So let's let KBF2 just for definiteness. You don't need, this graphical structure doesn't require that, but, and then what we're going to do, so we're going to use the fact that these two products, you've got 2 ways to multiply that that are interlaced, and what we realized was that you could kind of visualize products, especially because these are fairly free. I mean, I think it's true for any Hopf ring, you could visualize it in 2 dimensions. It's just that with relations, things kind of would become something else, and yeah, the visualization, the use would be more limited. So let's let x1 be, and let n equals well, not n equals 2, let the number of sets of variables be 2. Then x1 is, I'm going to call it an x empty block. So the cup product, not the cup product, but the standard product is like that. X1 squared is like that. Y1 is this. So of course, Y1 squared is this. And then you have things like x1 second divided power, I'm going to represent like this. And that's, of course, x1, x2. And the point is that this is really the second divided power because x1 times x1 is going to be twice. Once I symmetrize, I'm going to get x1, x2, but I have to symmetrize that, so I'm going to get twice x1, x2, which is x1 second divided power. And so you can keep going. There's x1, 3. I've started to, just to be consistent with the divided powers, we can think of it this way. There's some different choices for some of the, but then, for example, x1 induction product y1 squared looks like this. And that's this symmetrization of x1 y2 squared plus x2 y1 squared. Okay, and yeah, and so you get you have a dictionary between these symmetric monomials and symmetric polynomials and these diagrams. And what I'd like to do is go back and go through our calculations in this language. And again, the point is that this Hopf ring distributivity, well, let's see it in action in some of our examples. So I need to scroll back in 2 different places. And we're going to go through some of these first calculations, but I'll sort of indicate how you would see them in this graphical language as a way then to sort of bring in this Hopf ring perspective. Okay, so how would we see this calculation? Oh wait, I think I've got more scrolling to do. There we go. So this first calculation, of course, there's just one block type. Maybe I'll write in blue. Brown. There's just one block type. And what we find is that this calculation can be viewed as, that's the first polynomial. This is the second polynomial. And right, and the point is that this is, yeah, x1 plus x2 has 2 variables, so it's not just a single block, it's a symmetrization of x1 times 1. So x1 plus x2 is x1 induction product, the unit. Remember, I had said that I have to have the units in each degree. And so the way I say this graphically is with a little blank space. And this ends up being this polynomial in, oh, and actually this one here also is in 3 variables, but I've only got two, the product of 2 of them at any given time. So now this has, is exactly the representative of, you can start seeing that this is like x1 to the first, x2 to the first, x3 to the first, x4 to the 0, x5 to the 0, and then symmetrize. So that's one way to actually say what this dictionary is. Take any symmetric polynomial as a symmetrization of a unique monomial, where, say, the power of x1 is greater than or equal to that of x2, which is greater than or equal to that of x3. And if you just think of those numbers as a Young diagram, then we've got a sort of Young diagram here. Now, this is with one set of variables with, oh, and then also one set of variables here in this next example. So I would translate this as, so again, x1, y1 plus x2, y2 plus x3, y3. There I have only, no, I do have then 3 sets of variables. So, but sorry, then this goes like this. Okay, so I have the polynomial x1, y1 symmetrized up to S3 symmetry. And then this x1 squared plus x2 squared is this with x1 squared symmetrized up. And then this equals, right, so then it's again, the induction product is sort of stacking things next to each other. It's sort of, there's some commutativity there. And so, right. So what we could say really is recognize that the first one was x1, y1 times 1. The second thing was x1 squared, times 1 in 2 variables, one variable. And we get x1, y1, x2 squared, transfer 1, 3. There's a way to say what that one is. So yeah, so that's just the induction product itself in these 2 examples. Let me again start to talk about products through this example. X1 plus x2, I would call it empty block with that 1 to the right, because again, this is x1 induction 1 gives me x1 plus x2. This I would have 2 blocks. This one, of course, then we've got the filled in versions of these. And then E and F are interesting. E is, you've got the blocks of different colors stacked on top of each other, x1, y1. You could really think this as x1, y1 induction product with 1 gives you the symmetrization, x1, y1 plus x2, y2. This is more interesting, as I said before. I think of this one as more interesting. This is really x1 transfer y1. X1, y2 plus x2, y1. And again, I should say induction, not transfer. AB equals E plus F. So we're starting to get what the Hopf ring does in multiplication. So that really says that A times B equals, this starts looking like a Tetris game where if the blocks are coming down, I can, the white block can land on top of the filled-in block, or it can land next to the filled-in block. And again, there's some commutativity here, and we see that AB equals E plus F. A times B equals E plus F, as we say there. And then this final relation, which I didn't bother to write out, E times F, so that means taking this second degree polynomial times this second degree polynomial. And again, it's the same thing, but the way I would put it is actually, once again, it's like a Tetris game. I can either have the two dark and the light and the light, which if I want, there's again some commutativity. I can think of this diagram alternatively like that. Plus, if I stack in the other place, I've got two lights on top of the dark. And then this is A squared D would be two lights on top of the dark. And B squared C is going to be this. So you start, rather than the longhand, you start appreciating the way these blocks and the Hopf ring structure work out. Again, the paper with Paolo and Chad sort of gives the details of the definitions. Give one more example here. Let's work in this space over here. Let's see, so x1 squared y2 plus x2 squared y1 times the transfer product of x1 cubed with x1 y1. Okay, and again, rather than the distributivity, let me just say the way the multiplication ends up working is you match the columns of each, so I can match this with that and this with that, or in the second way I can match this with that and this with that. And so if I match up the according to the greens, then the first column is going to have 5 whites, and the second column is going to have a white and 2 darks. And then if I match according to the yellow matchings, then the first column, let me show more, then the first column, let's see, according to the yellow, then I would have 3 with 1. Let me do it this way. And the second column would have also 3 with 1. And there's that factor of 2. Because these columns are, those results are symmetric. Great, I think those are sort of all of the examples. Hopefully this is enough to appreciate that this theorem tells you then how to multiply symmetric polynomials. It gives you an additive basis. So let me just, a couple final words. So Hopf ring distributivity implies that you can so a key to understanding where these diagrams are really coming from is that you can reduce to some sort of times product, induction product, another standard product, induction product, again, another standard product. Keep on going. Just like in a usual ring, of course, any product of polynomials is monomials. Any product of Hopf ring monomials, any product of Hopf ring elements can be reduced to these kinds of Hopf ring monomials. And again, if we want to think about sort of x1 cubed, that's, you know, this kind of induction product, again, there you would, we can go through the definitions, but I'll just go through the graphics. You get this kind of diagram. So yeah, so Hopf ring distributivity allows you to reduce to Hopf ring monomials. These Hopf ring monomials have this graphical representation. And so you can fairly quickly go to, if you've got a good Hopf ring presentation, means it's easy to get an additive basis plus multiplication rules. What's harder, and we'll discuss maybe even more in further talks where we get more into how this shows us what's going on for cohomology symmetric groups, is to, if you really want generators and relations, for example, that can be combinatorially involved. I mean, you obviously can at this point, if you have an additive basis and multiplication rule and a nice filtration, you can just take your first non-trivial element, that's a generator, you take away all its powers, you can see what the next thing in the next degree that's not, hasn't been removed, that's another generator. You take all products of those first two things, you remove those, and then you take your next element, and that's a third generator. So you can, it's quote unquote just combinatorics to get generators and relations, but that's complicated. The nice thing is that these multiplication rules, additive basis and multiplication rules, can sometimes do things that you would want to do with generators and relations. For example, to understand ideals, you can, in some cases, and Chad and I do this to study alternating groups, starting with symmetric groups, we understand that ideal structure, some quotient structures, other structures that you'd want to do with commutative algebra, we do with this Hopf ring kind of commutative algebra. So yeah, I'm going to end there and see you another time. Sorry.